Chronic glycemic disorders, like diabetes and hypoglycemia, require regular monitoring of blood glucose levels. From fingersticks to interstitial monitors, all current market solutions utilize invasive or else semi-invasive methods. This means that those living with chronic glycemic disorders must regularly deal with the pain of needles and the waste and expense of disposable monitoring supplies. At present, there is no way to measure blood glucose without invasive methods. The non-invasive blood sugar monitor, or NoBS, is a non-invasive monitor that uses a machine learning model to assess blood glucose levels from an input of bioimpedance analysis and multi-wavelength photoplethysmography, mPPG. The monitor then stores the data it collects remotely on its own server and displays the data via a specially designed mobile application to allow both health professionals and users to view glucose data and make informed decisions about treating chronic metabolic disorders. The device is based on a wealth of previous research regarding non-invasive glucose analysis, and as stated, it relies on two types of non-invasive sensing. The first, mPPG, is a form of spectroscopy that gathers data about the bloodstream by emitting light waves through the finger and then analyzing the reflection and absorption of the finger. The NoBS monitor measures mPPG at 3 distinct frequencies, as shown here. The second sensing method, bioimpedance, measures the reactance of the skin, flesh, and blood by passing a weak electric current called the stimulation signal through the user's finger. By measuring the effects of the finger on the magnitude and phase of the stimulation signal, we can gather information about the makeup of the bloodstream. The NoBS monitor measures bioimpedance at 5 distinct frequencies, as shown here. These, along with an ECG signal for blood concentration measurement and heart rate, are fed into a custom-built machine learning model, which we will cover in a bit more detail later. The machine learning model interprets these raw signals into an estimation of the current blood glucose level and passes this to the next stage. At this point, the NoBS server calculates heart rate and breathing rate from the ECG signal and passes these, along with the machine learning model's assessment of blood glucose, to the mobile application for user and physician viewing. The application displays these current estimates and a graph showing the values of previous readings up to the current time. The preliminary results of the NoBS project speak for themselves and are only limited by the small amount of data that the team has been able to test on thus far. Our machine learning model is designed with 2 convolutional layers and 3 dense layers with a 25% dropout to prevent overfitting to neurons. Additionally, we used hyperparameter tuning when training the model to ensure the best architecture for the job. Around 1 million data points were taken from a single subject and used for training and validating the machine learning model. Using a data set separate from that used for training, the machine learning model was able to determine blood glucose levels with a root mean squared error of 10.2 milligrams per deciliter. This is less than an 8% difference from the actual values of glucose on average. The NoBS team is made up of the UAH Computer Engineering undergraduate seniors Elijah Moore, Charles Gould, Garett Sutton, Caleb Doughty, and Alex Thomas, and has been mentored by Dr. Emil Jovanov. Over the course of the project's lifespan, much has been achieved, including, but not limited to, the end-to-end construction of a machine learning model for physiological data analysis, the development of 3 custom PCB boards, the development of a custom mobile application and server, and the development of a full codebase for the MAX 30009 bioimpedance analysis chip. Though this prototype is not a ready-for-market device, it is our hope that the NoBS project will be an instrumental piece in advancing the field of non-invasive physiological analysis and in making strides towards truly needle-free treatment of chronic glycemic disorders.